Here's another question where they're asking us to find enthalpy of the standard enthalpy change for a reaction using enthalpies of formation that are listed in Appendix 4. It's much like the previous question, except there is one little tricky part in part B of this problem. So again, our equation is the summation of the heats of formation times the coefficients for all of the products minus the summation of the heats of formation times their coefficients for all of the reactants. So for the equation in part A, we have 3 water molecules. So 3 times, and note the state of matter here, gaseous water is different than liquid water. We have negative 242 for gaseous water. And we're adding to that carbon dioxide's heat of formation, negative 393.5. Alright, that's the products. On the reactant side, we have liquid ethanol, coefficient of 1, so negative 278 times 1. And we're adding to that for oxygen. You could look this up, or you could just know if you have a diatomic molecule, the heat of formation is 0. Once you've got the equation set up, it's just a matter of crunching numbers. It works out to be negative 1235. And you can state the unit either as just kilojoules or kilojoules per mole. The per mole bit means per mole of the chemicals listed in the balanced equation. So if the coefficient is 3, the energy change is negative 1235 for every 3 moles that participate in the reaction. Okay, part B is the tricky one. If you try looking up aqueous hydrochloric acid, you won't find it in Appendix 4. And the reason is aqueous hydrochloric acid never exists as intact molecules. It's a strong acid. Strong acids, when dissolved, are completely broken apart. So you could think of this as, instead of hydrochloric acid, you actually have 4 hydrogen ions and 4 chloride ions. Let's rewrite the equation with that in mind, and then we can look up the numbers in Appendix 4. This time we're dealing with liquid water, not gaseous water. And I'm writing the ions that comprise hydrochloric acid as broken apart. Okay, if we apply the equation then, for products, we've got silicon dioxide, that's 1 times negative 911 for the hydrogen ion, 4 times 0 for the chloride ion, 4 times negative 167. And we're subtracting from that the reactants. Silicon tetrachloride is negative 687, and liquid water is negative 286. Once you've got this set up, it's a matter of just crunching numbers. And let's see, this one works out to be negative 320 kilojoules, or you could state that as kilojoules per mole. Part C, we have magnesium hydroxide as the product. That's negative 925. And from that we're going to subtract the magnesium oxide and liquid water. Notice I'm multiplying by the coefficient of 1. Even if it's implied, I think it's a good habit just to show there's implied coefficients of 1, and so I'm multiplying all of these heats of formation by 1 as well. When you crunch those numbers, this one works out to be a negative 37 kilojoules, or you could state it as kilojoules per mole.